They will highlight some of the new dialysis membranes for new indications. Our agenda will be dialysis membrane structure, porosity, hydrophilicity, and geometry, absorption, pros and cons, and finally going to the medium cutoff and the high cutoff clinical values. The dialysis membrane structure constitutes of an inner layer called the skin layer or the filtration layer. It's around 1 micron, and a very supportive layer with a porosity bigger in the outside than from the inside. That's why it's calling asymmetric dialysis membranes. The inner layer and supportive layers, the inner skin layers or the sieving layer is around 1 micron, constitutes of the BVP, defines the molecules that can pass the sieving criteria, should be smooth as an endothelium with an overall area of the blood contact is just 1 micron. Thrombogenicity is important to be determined because the roughness inside the filter fibers makes the thrombogenicity and the coagulation activation. The ideal membrane should be biocompatible, less thrombogenic, optimum ultrafiltration for convection therapy and hemodiafiltration, excellent diffusive and convective properties, optimum permeability, and excellent sterilization like in steam sterilization. The dialysis membrane hydrophilicity is important. Optimizing the surface roughness, decreasing the coagulation activation and thrombogenicity with optimum port size and port size permeation for different uremic toxins. So the hydrophilic surface of the fiber is essential for all current modern dialyzers for improving the blood membrane contact. The dialysis fibers make up meaning that perfect fiber arrangement, maximizing the blood flow distribution inside, optimizing internal flow, excellent blood and dialysate matching, so no dead areas. Increasing the blood flow inside the headers, improving the flow inside the fibers is importantly as well. And this fiber number, more than 10,000 per dialyzer for adult filter, should have a smooth flow inside all through the dialyzer length with perfectly inlet and outlet flow parameters. So these are called the fiber arrangement and geometry, with importantly improving the speed inside the flow with different types of caps or the flow design inside the fiber. The geometry with flow design, the blood dialysate matching, no dead areas, and this could be an excellent or ideal dialyzer with perfectly flat, higher surface area for adults. Steam sterilization is better, higher performance clearance value, sieving coefficient, and less clotting. No sterilization residual, like in steam, better than ethylene oxide, higher pyrogen retention, so no pyrogen transfer from the dialysate, easily priming and wash out or rinse back. When a dialyzer is innocent, if imperfectly priming, inadequate anticoagulations, small size for patient weight, low blood flow, recirculation in the vascular access type, or short dialysis time. Highlighting here, importantly, the cardiopulmonary bypass, where the blood coming from the heart going directly to high flow arteriovenous fistula, bypassing the systemic tissue. Subsequently, removal of toxin from the tissue is impaired, and this means higher rebound. The blood and the dialysate matching is important as well to have no dead space inside or in between, and perfectly described in the microundulation characters, where 100% of the fiber are facing the dialysate. No streaks, that means that perfect flow and hydrophilicity, or definitely may be due to patients-related factors like recirculation or higher coagulopathy. So the dialysis membrane in general should have a higher filtration rate for convection and the hydrophilicity with defined membrane cutoff. And this poor density or poor diameter in angstrom defines the ultrafiltration the permeability and the sieving coefficient by just the pore diameters inside. And this flow of the blood defines the sieving coefficient curve, again according to the pore size. We have three examples here: the high flux, the medium cutoff, and the high cutoff dialysis membrane. The difference between the three is the pore diameters in angstrom, while the high cutoff or medium cutoff are more protein leaking, meaning that more albumin loss. So definitely higher sieving characteristics of both membranes, meaning higher albumin loss in this area, depending on the type, maybe from 3 to 7 grams per session, depending on the type of the membrane. So the sieving coefficient should be identified for each type of dialysis membrane. We can have remarks on that, and it is definitely reported to be the pore size distribution, and all the criteria between the two arms from the standard pore size in the high flux and the higher porosity in the high cutoff. Looking to that, the pore diameter or pore radius are definitely higher for the high cutoff pore diameters. All the profiling that should be available for nephrologists, considering three parameters: the albumin, the beta-2 microglobulin, and the myoglobin sieving coefficient criteria. Again, the hydrophilicity is an important factor in choosing the perfect dialysis membrane, because membrane clogging or obstruction in hydrophobic membrane coming to the what's called the adsorption effect on the dialysis membrane, making the protein's adsorption clogging the filtration force and decreasing the sieving coefficient curve with time on dialysis, meaning that within a 30 minutes of starting hemodialysis can plug. While higher blood flow or shear stress can have a positive effect on protein adsorption by moving the proteins away from the internal side of the fiber. With higher blood flow, we can remove protein deposition, but against that is the membrane integrity or the BVP illusions, and increasing the ultrafiltration rate by higher blood flow necessary for hemodiafiltration techniques. Pressure drop is important in back filtration effect. That's why we have to use ultra pure or sterile dialysis. The internal diameter is important, especially in convection therapy, because it guarantees smooth blood flow inside the fibers. With different types of dialysis membrane criteria, we can choose in between them accordingly to the criteria required. Definitely in myoglobin, character of the sieving is better for sepsis or in patients with myeloma, for example, to remove higher uremic toxin retained. It is not consistent, the sieving coefficient. For example, the albumin, it starts very high, then drop with time, because after 30 minutes, protein absorption is high, so albumin loss is low. Beta-2 microglobulin usually stable all through the cycle or the session period, while myoglobin drop from the start to the end, denoting that protein clogging. So uremic toxin and its value going to low flux to medium cutoff in the current use, I think hemodiafiltration has generally acceptance nowadays for most of nephrologists. The effect of adsorption has a constant process, because you can remove more protein bound uremic toxin by adsorption to the membrane, but against that is the filtration failure, as clogging inside the filter increasing with time, especially after 30 minutes of the dialysis therapy. So protein adsorbed on the wall, clogging the porosity and impair the filtration capacity of the dialyzer. So hydrophilicity is generally accepted than in hydrophobic criteria, and choosing the bigger dialyzer is important in hemodiafiltration, especially to have more filtration effect and more convection volume required. So in conclusion, in this part, the filter or fiber criteria defined as permeability or flux, and flux meaning water and solid, and water defines the hydraulic movement of water with the TUF or the ultrafiltration coefficient, while the permeability of solid meaning that achieving to different molecular weight size. In general, albumin loss is accepted to 3 grams, while we have to look for the low sodium albumin in patients due to inflammation, nutrition, or loss in dialysate, loss in the gut, or the dilution effect due to volume overload state. Different dialyzers have different albumin leak, and this value increase in hemodiafiltration. So adsorption can improve middle molecules, but on the other hand, this adsorption block the filtration effect, and to my opinion, it is of lower requirement during dialysis because we need more filtration than adsorption. The best example of that is the polymethyl methacryl membrane, which is a high adsorption capacity, unlike the polysulfone, and this makes protein cake, and this protein cake will decrease the ultrafiltration, decreasing the clearance, with building up and increasing in the transmembrane pressure during the session. So this is a difference between different dialysis membrane in the adsorption. So the removal in adsorption is different by different dialysis membranes, while it's very high and increasing in hemodiafiltration other than in high flux dialysis due to increasing in the pressure and increasing in the transmembrane pressure, increasing the protein adsorption, making that very difficult for filtration with an adsorbed protein as well blood cells. Moving these proteins away from the blood side, making the filtration return it back to its starting time. Finally, we can in brief describe the difference between high flux, medium cutoff, and high cutoff dialysis membrane. In general, there is acceptance for the medium cutoff to removing molecular weight beyond the high flux filters or membranes up to 45 thousand Daltons or kilo Daltons, and this is in particular in lambda and kappa light chains, not necessary in myeloma because they are considered nowadays as a relic toxin, improving in the overall saving coefficient of the medium cutoff over the routinely used high flux, but on the expect that higher albumin loss. So this is a randomized controlled trial of medium and cutoff for the quality of life and hemodialysis patients with different dialyzer types. However, the significance in the biomarkers and dialysis adequacy is insignificant between both. And after 12 weeks of the dialysis with medium cutoff, the significant difference is not to much extent that we can reach, just improving in marginally in the kappa and lambda light chain. The overall quality of life did not significantly change, and just few improvement in pruritus between patients groups of high flux and medium cutoff dialysis. We need a long-term randomized controlled trial to have the medium cutoff the benefits. The high cutoff are not used in clinics routinely. In multi-studies, randomized controlled studies, had been assessed the difference between high cutoff and high flux in different aspects and different studies. There is marginal improvement, and this impact of high cutoff hemodialysis on hemodialysis independent at 90 days in patients with myeloma, improving partially than in the high flux group. Going to one of the important clinical application nowadays is the hemodifiltration, the doses and barrier and special requirements for the dialysis membranes. Hemodialysis and hemodifiltration technique is considered the hardest point on the hemodialysis membrane. It's a very forceful convection volume with an inline substitution of infusate. This makes too much burdens on the dialysis membrane with dragging forces to remove the higher molecular weight from the blood side and carries both the diffusion and convection. So convection in hemodifiltration is extremely high, reaching about 25 liters in the post-dilution mode of hemodifiltration. And this convection needs too much of water removal and subsequently increasing in the transmembrane pressure. And this hard kicking out the dialysis membrane by the higher hematocrit and the higher protein content, what is called the protocrit. So the hemodifiltration using a very high ultrafiltration rate to remove the higher and bigger molecular weight toxins by the dragging forces, and the pressure inside the filter is extremely high due to increasing the demand for removal of water. Needs very high transmembrane pressure to drag solids from the blood side of the dialysis membranes with an average of about 300 millimeter mercury. The randomized trial on clinical performance and biocompatibility of many of the high flux dialysis membranes in either hemodialysis and hemodifiltration reveals that if we are considering the same dialysis membranes, the differences between both of them is clinically clear. You can see that even for the same dialysis membrane, the removal and reduction ratio, for example, the free lytic chain is higher by hemodifiltration technique. This is simply due to increasing in the transmembrane pressure. And hemodifiltration simply is the commonest technique nowadays for advances in uric toxin removal, and it removes the small solids, the middle molecules, and the higher molecular weight molecules. In our clinical studies in Shamsi University, we always go to the higher surface area of the dialyzers because the transmembrane pressure differs between the start and the end of the dialysis session. So we usually go to beyond 2.0 square meter for hemodifiltration. And in our studies as well, we found that with online hemodifiltration, there is improvement in the DNA methylation and indoxyl sulfate removal. And this is completely a dose dependent on the substitution volume in the post-hemodifiltration technique. So bigger surface area dialyzers are now in the field with up to 2.6 square meter surface area, increasing the convection volume with larger dialyzer surface area and the higher KOF is considered now an ideal for hemodifiltration, while decreasing the convection volume could be related to low dialyzer surface area and ultrafiltration. What is in our experience the hemodifiltration? We understand the filtration fraction, it's out of the scope of this talk, but we need higher filtration fraction and higher blood flow with perfectly sieving coefficient of dialysis membrane. And there is a lot of limiting factors for high volume online hemodifiltration, in particular dialysis membrane required. So dialyzer fit for hemodifiltration should be bigger size with increasing in the internal diameter to avoid coagulation and avoid protein absorption, higher sieving coefficient. We need as well good vascular access. And using the automatic mode for the hemodifiltration the machine feedback control the higher transmembrane pressure, so avoiding the absorption and functionality of dialysis membrane, increasing the filtration fraction, definitely will have a negative impact on the coagulation as well protein concentration and the protein deposition on the dialysis membrane. So there is a lot of relation between ultrafiltration and transmembrane pressure in hemodialysis filtration. We increase the parameters like blood flow, increasing the filter geometry, filter size, flow resistance, and improving the patient parameters as well, in particular the vascular access. Coming to the end with different sterilization types, to my opinion, steam is the perfect one with either autoclaving or inline, and this improving sterilization, double filtration, efficient time to maintain a continuous steam flow for sterilization effect. So, Mr. Chairman and dear colleagues, in my conclusion, membranes are in progress of more porosity and higher saving coefficient. Dialyzer fiber makeup is essential for great performance, and we are all awaiting for the magic solution of bioartificial kidney to have a real renal replacement therapy.